Humanity has always been advancing. We took 1 million years to advance from just fire to using stone tools, 100,000 more years to create wheels, a further 10,000 years to the invention of the printing press, then 1,000 years to the use of electricity, 100 years to the innovation of flying and computers, and a mere 10 years to being able to edit human genes. Today, technology has advanced so drastically that the printing press has evolved into an automated printer that creates physical, three-dimensional objects from a digital design. Technology is advancing at an alarmingly rapid rate, with society only having scratched the surface. In light of the fast-paced advancements, the risk of falling behind is inevitably a concern. Within the field of occupational therapy, technology has played a defining role in practice from the beginning establishment of the profession. Upon studying the profession's literature, it is evident that technology forms a fundamental contribution in enhancing an individual's occupational engagement, which is the backbone of our profession, through what is known as assistive technology. With the Fourth Industrial Revolution and resultant advancement in technology, the importance of incorporating technology within practice settings is emphasized. The use of 3D printing within the healthcare sector is numerous and expanding. Within the field of occupational therapy, however, the global literature is minimal, and within the South African context, and KwaZulu-Natal specifically, absent.
The problem is that within this specific context, there is limited research examining 3D printing within healthcare and currently no existing research examining 3D printing and the perceived acceptance of 3D printing by South African occupational therapists. This is alarming considering the number of people with disabilities within our context and the role of an occupational therapist. The primary concern of an occupational therapist is to enable individuals to overcome barriers as a result of their disability. Technology presents hurdles in our current practices, however, it also provides new opportunities and possibilities in enhancing and enabling engagement and meaning in life. It is therefore recommended for therapists to engage beyond our typical discipline to advocate for our patients. This displays a gap in the literature and thus a barrier to potential advancements in therapy, technology integration for future practice across South Africa, and a potential barrier to assisting individuals with disabilities in our ever-changing environment. Before we get into 3D printing, we're going to be looking at various types of manufacturing. There's casting, forming, subtractive manufacturing, and additive manufacturing, to name a few. Today we're going to be focusing on additive manufacturing, which is a type of layered manufacturing whereby items are fabricated in consecutive layers. 3D printing is a type of additive manufacturing. So, what exactly is 3D printing? 3D printing is also known as additive manufacturing. 3D printing technology is a method of manufacturing a three-dimensional object by progressively adding materials layer upon layer until a complete object is formed. The consecutive layers are guided by computer-aided design, also known as CAD. CAD is a computer software that enables us to design objects. It enables us to create or modify and enhance 2 or 3D designs. This software replaces manual drafting or sketching with an automated process. Let's take a look at the history of 3D printing. Where did it start, and how did we get to where we are today? A review of literature will reveal that there are multiple key patents that form the core competencies of 3D systems. Between 1972 and 1986, 3 individuals formed the beginnings of what we call 3D printing today. In 1988, Scott Crump invented an additional 3D printing technology called fused deposition modeling. Thereafter, for roughly 20 years, 3D printing technology continued to quietly evolve but remained in the hands of large stakeholders, as it was not easily accessible. In 2005, however, with the development of the RepRap project, things began to change. Dr. Gordon started this project, which consists of an open source community with the primary goal of making 3D printing technologies more accessible. From that project, 3 avid participants went on to start their own 3D printing companies and founded the MakerBot in 2009, which became one of the first consumer 3D printers. Now, fast forward almost 2 decades, and the application of 3D printing has expanded exponentially, now being utilized in commercial, academic, and clinical environments. Additive manufacturing processes. It is important to understand that 3D printing is the umbrella term to describe a group of additive manufacturing processes. In other words, 3D printers can create the 3D objects in different ways, using different processes, and operate differently, but they all have one thing in common. The end product is created layer upon layer. The different processes include material extrusion, vat polymerization, powder bed, material jetting, binder jetting, direct energy deposition, sheet lamination, and micro 3D printing. Today we'll be focusing on material extrusion. This process involves material being ejected through the nozzle of the printer. The material is pushed through a heated nozzle, and as a result, it melts. The printer then deposits this melted material onto the print surface or the print bed, where it creates the desired object, layer upon layer.
We are now going to take a look at the different parts of the 3D printer. 3D printers generally work along 3 axes, the X, Y, and Z axis. Each axis makes use of a motor. The 3D printer's lateral movement is assigned to the X and Y axis, while the Z axis corresponds to vertical motion. Printers may vary in parts and setup, however, this will be a general overview of some basic parts. On the top left, you will see an arrow pointing to the Bowden tube. This tube guides the material into the extruder of the printer. The extruder is part of the printer that pushes out or extrudes the material. It is made up of a motor that turns and slowly pushes the material out through the nozzle. The nozzle, or the hot end, is where the plastic is melted so that it can be used to form the 3D object being printed. The temperature of the hot end can be adjusted based on the type of material being used. On the right, you will see the print bed. This is the surface on which the item is built. It is also heated and allows the object to stick to the surface so that it doesn't move around during printing. The controller is generally a small screen. It is where information about the print is displayed. It also allows for settings to be changed and items such as a memory stick to be plugged in. Before looking at the potential for the use of 3D printing technology within the field of occupational therapy, let's take a look at how the technology is being used within other areas of healthcare. There are a variety of potential and actual applications for 3D printing technology in many professions within the medical field. The use of the technology in these fields has much to do with the possible benefits it provides, including potential for customization, personalization, cost effectiveness, and increased productivity.
We will be looking at applications in prosthetics, surgery, printing human tissues, imagery and planning, audiology, dentistry, patient education, and pharmacy.
"3D printing technology is already widely used within the field of prosthetics. Prosthetic devices that have been 3D printed can be customized according to patient needs as well as individual taste, and cost significantly less than traditional alternatives. The low cost of a 3D printed prosthetic is especially important in the pediatric population, where children are outgrowing their prosthetic devices at a rapid rate. An important factor about 3D printed prosthetic devices is their aesthetics. Research that involved asking amputees about their demands found that, in addition to obvious answers like lightweight and simple operation, they did not feel that a device should necessarily visually represent a human hand. For example, some may prefer superhero hands, Star Wars gadgets, etc. 3D printing provides opportunity for customization, enhancing patient satisfaction and acceptance of the device. An example of how 3D printing technology can be used within this field can be seen in the following video, where a movement called Not Impossible 3D prints a customized prosthetic upper limb to help an impoverished war victim.
I don't believe that you can fix someone. That was never my goal here. Daniel was 14 when the bomb hit. Hiding behind a tree saved his life. But after losing both of his arms, he said he wished it hadn't. He had lived 2 years without arms. Daniel is just one of over 50,000 amputees left in the wake of the bloodiest war Africa has ever known. The plan was to go to Sudan and 3D print prosthetic arms for Daniel. But that was just the beginning. We wanted to leave his village with the tools and knowledge of how to create these prosthetics long after we had gone.
This is going to be the hand that we work on for Daniel.
I still pinch myself the fact that I was able to teach a group of people to print. Many who had never worked with computers before and never seen a 3D printer before, and I taught them how to make arms. That's what technology has the potential to do. I have a process. And the process is you commit, and then you figure out how the heck you're going to do it. The second I saw the story about Daniel, I didn't need to reread it. When you look at a picture of a boy with bandaged stump arms, I mean, what do? Do you just, oh, that's too bad, and close the computer and go to bed? What do? You can't put the pieces back together in someone else's life. But maybe if we print them new pieces, they'll start to learn to put them back together themselves.
In the surgical field, 3D printing has also been widely used to produce implants used in surgery. Today, several manufacturers produce high-quality replacements and implants for the spine, hip, pelvis, trachea, and skull, to name a few. With CAD software being compatible with patient imaging, medical professionals now have the ability to create customized prototypes and devices that can be implanted during surgery. The implants are patient-specific, as the use of patient imaging allows for the shape and size of the object to be individualized and precise. A variety of CAD software programs have been created for use in this area that support MRI, CT, and ultrasound. An example of a free downloadable software is seen on the screen. This is Invesalius, which allows for users to create printable 3D designs from medical imaging. In addition to saving time and money, 3D printers can be used to create unique characteristics in surgical implants. There is the potential to design complex structures for implantation and even include slow-releasing drugs that can improve the healing process. Another exciting and rapidly expanding area of application for 3D printing technology is the manufacturing of human tissue by 3D printing cells. The ultimate aim for the use of 3D printing in this area is to reduce the shortage of supply in the organ donor market. It has been recently discovered that there may be the potential for 3D printing using stem cells, opening new possibilities in this area. Flat tissues, such as skin, tubular structures, such as the trachea or urethra, and hollow, complex, solid organs, such as the liver, have been 3D bioprinted to date. In addition to 3D printing with cells, a device called a biopen allows surgeons to repair damaged bone and cartilage during a surgical procedure by drawing new cells directly onto the bone in real time. Applications of 3D printing technology for imagery and treatment planning have been explored in a variety of professions within the medical field, such as radiation therapy and surgery. In the field of radiology, radiologists can select objects of interest by isolating structures on images and scans. Once isolated and saved in a specific format, these objects can be saved as 3D designs that can be 3D printed. 3D printing technology has been used to create models to use for treatment planning in radiation therapy. This allows for greater accuracy when administering treatments. In the field of surgery, 3D printing has provided opportunity for surgical planning that is patient-specific. By creating unique patient-specific models, simulation is possible. Planning can be done for surgical entry points, screw direction, and placements and surgical lines. The creation of 3D printed models helps visualize complex anatomy, and the time saved from surgery planning has resulted in prevention of further blood loss and reduced operating times, ultimately resulting in improved patient outcomes. 3D printing has been beneficial in education for many years. It has been used in education for anatomical models. Medical students have been able to use 3D printed anatomical models in education with fewer financial, ethical, legal, and cultural concerns as occurs with cadavers. The field of audiology is one profession in which 3D printing has been used extensively to date. According to research, there are currently more than tens of millions of 3D printed hearing aids in circulation worldwide. 3D printing has transformed the manual, labor-intensive process of manufacturing hearing aids into an automated one that is fast and patient-specific. Before introducing 3D printing into this profession, manufacturing of hearing aids was time-consuming and often took more than a week. Today, the 3D printing process for manufacturing hearing aids that involves scanning, modeling, and printing can take less than a day. In the field of dentistry, by combining oral scanning, CAD design, and 3D printing, dental labs can accurately and quickly produce models and orthodontic devices. Instead of uncomfortable impressions, a 3D scan is taken, which is later transformed into a 3D model and sent to be 3D printed. The designs can be stored digitally as a 3D CAD file. 3D printing technology therefore eliminates physical impressions and the storage of these models. Looking at the concept of patient education, the fields of prosthetics and surgery have also used 3D printing concepts to better educate and treat patients, resulting in optimal patient outcomes. 3D printing also helps improve patient education, as a physical 3D model allows the patients to better visualize their anatomy and the procedure taking place, as opposed to viewing complex 2D MRI or CT scans. There has been significant improvement in informed consent as a result of this. Lastly, in the field of pharmaceuticals, there is the potential to 3D print pills from recipes piped directly into the 3D printer. The first 3D printed drug is known as Sprintam for epilepsy treatment and has obtained FDA approval. The use of a 3D printer allows for a very porous pill to be manufactured due to the structures that can be created. This allows for fast dissolving and easy ingestion. It must be noted that the use of 3D printing in this area poses serious legal concerns, in a similar way to how the introduction of music downloads caused disruption in the music industry. Let's take a look at the applications of 3D printing in occupational therapy. Occupational therapy has evolved significantly since originating in the 1900s from the arts and crafts movement and the treatment of war veterans. With the Fourth Industrial Revolution and continual rapid strides in advancements, it is important to consider the effect that each stride has had on our profession, and how the advancements can be utilized to benefit our profession and the patients in our care. The Fourth Industrial Revolution may bring about unique challenges for our profession. However, it also has the potential to create novel opportunities. As occupational therapists, we have a responsibility to adapt and explore the inevitable changes that come with continual innovations, in order to ensure that the profession remains relevant and abreast with the rapidly changing environment we are working in. With the rapidly changing environment, some might experience fear of automation due to concerns surrounding their role and relevance. In a study, occupational therapy in the Fourth Industrial Revolution was unpacked. As occupational therapists, our core competencies include client-centered therapy, critical thinking, complex relational engagement, problem solving, and very importantly, the therapeutic use of self. These core competencies make it difficult for occupational therapy to be replaced by automation. However, these advancements certainly have the potential to alter the way in which we provide services. In an Oxford University study titled The Future of Employment, 702 different but common occupations were examined, and they determined that occupational therapy is only at 0.35% risk of automation. One aspect of occupational therapy practice in which the technology of 3D printing has been explored is in the fabrication of splints and orthotics. The process of fabricating more complex orthotics can be a laborious manual process. Traditional procedures for splinting include cutting, heating, and molding thermoplastic material to the desired shape for the specific function. The time requirements, fit, comfort, and aesthetics are to a large extent dependent on the therapist's level of skill and experience. In a study comparing 3D printed splints and traditional thermoplastic splints, the printed splint was said to address nearly all reported deficiencies of conventional splints. The 3D printed splints were described as lightweight, waterproof, well ventilated, and aesthetically pleasing when compared to traditional thermoplastic splints. CAD software is used to create the orthotic designs. These can then be distributed extensively using large online open source communities, with the end user having the opportunity to customize the model to meet specific patient needs. The use of open source, customizable 3D printed orthotics creates the potential to significantly reduce costs involved in manufacturing customized thermoplastic devices. Another potential benefit associated with the technology is the opportunity for patient feedback prior to printing during the CAD process. This leads to greater patient involvement, provides a sense of autonomy, and ultimately may improve patient satisfaction and compliance, reducing wastage. As we as OTs know, assistive technology devices include specifically designed and generically available products facilitating participation of individuals in their daily occupations. Assistive devices are often available commercially. However, these generic devices often do not meet the unique needs of the patient. Often, occupational therapists are required to make significant customizations or to fabricate new designs of assistive devices to enable functionality. The application of 3D printing in the manufacturing of assistive devices is not to reinvent the wheel. It is one of many ways to easily and effectively customize the design and may offer more durable and cost-effective solutions when compared to conventional methods. There are many examples of how 3D printing technology can be incorporated into occupational therapy and rehabilitation practices. One example is depicted in a study where 3D printing was used by a prosthetic team to manufacture and test a unique assistive device to assist a patient with a partial hand amputation to play his French horn. The team used 3D scanning of the limb and transferred the file into CAD software to design and manufacture the device. This ultimately proved to be an effective method for designing, testing, and manufacturing this unique assistive device. The 3D printed assistive device was shown to be successful when assessing patient satisfaction, functionality, as well as cost when compared to traditional manufacturing. There are many examples of applications for 3D printing in assistive devices in occupational therapy. Some examples can be seen on the screen. However, a few more in-depth examples can be seen in the handout given to you at the beginning of the session.
When she was born, her legs were up by her ears and her shoulders were internally rotated, and she had ulnar deviation on her hands and rocker bottom feet. The geneticist came upstairs and told us she had arthrogryposis multiplex congenita. They brought her legs down and they casted her, and slowly and surely she started to develop. Our first year with Emma, we found out that there was going to be a conference, and it was in Philadelphia.
It was an arthrogryposis family meeting in Philadelphia where I described the Rex.
We watched a presentation on the Rex.
And that's how it all started.
We ended up in Tarek and Whitney's workshop.
The Rex was attached to a stand, and she was able to put her arms into the Rex and for the first time be able to lift her hand up towards her mouth.
She just started, throwing her hands around and playing.
We were bringing candy up for her to eat, and we were bringing toys up there, and it was so fun for us to go up there and to see her play.
The existing Rex, it's all metal parts, and it's kind of big, and Emma was too small for that. So we required something light and small that would attach to her body and go with her. So that's where we had this Stratasys 3D printing machine, and we thought, well, we could print it out for her.
And he did it, and the weight difference is significant. And for a child who only weighs 25 pounds, it makes a big difference. Whitney and Tarek put their minds together and came up with a jacket, and they would put the Rex on that, and we're on our second jacket. She outgrew the first one, and now we're on our second one. And it's still evolving. It's still growing into this incredible prosthetic that helps her to use her arms.
Without the 3D printer, we would not be in a position we're in with these younger kids, making them a Rex device that can go with them.
This is one of those industries that matches perfectly with 3D printing, additive manufacturing, because we need custom everything.
I think 3D scanning and printing technology is the future for this field.
The ABS plastic that they use is the same plastic used in Legos. It's human-friendly, if you will. It's really strong and durable to handle the abuse. We can answer a need in a heartbeat.
If the Rex breaks, all I have to do is take a picture and email it to Whitney. He knows exactly what the piece is. He prints it out. I go to the hospital, or he's even mailed them.
I don't have to worry about lead time to machine something, order supplies. I can just basically go back to my program and print out another one.
And it's back together and it's working. When she started to express herself, we would go upstairs and we would say, Emma, we're going to put the Rex on. And she called them her magic arms. And everyone in the room cried.
We took it off of her on this one occasion to make some adjustments to it. And as we took it off, she cried out, "I want that." And we didn't think all that much of it. But when Mom started to cry, and we look over and ask Mom why she's crying, and she kind of takes a moment to recompose herself and tell us that that was her first complete sentence. To be a part of that, a little special moment for somebody else, can't help but kind of tug at your heartstrings.
Let's take a look at the different types of materials used in 3D printing. The materials most commonly used are divided into two main categories. The two main categories of materials used in 3D printing can be seen in the video on the screen. As you can see, the grey part of the glove is made up of a rigid material that does not bend when the hand moves. The parts in between the grey parts are made up of flexible material that bend as the finger joints bend and move. Rigid and flexible materials. One type of rigid material is ABS. This is a strong, rigid material. It is the same type of plastic that is used in the water pipes of most homes. Some pros of this material include its low cost, smooth finish, good heat resistance, and good resistance to wear and impact. These properties make it a great choice for outdoor and high temperature applications. Some cons of this material include the potential for warping, shrinkage, and requirements for heat due to its heat resistance. One of the most commonly used materials is PLA. This material is easy to use, inexpensive, and has a variety of potential applications. Some pros of PLA include its low cost, good strength, less shrinkage, and good shelf life. Some cons include a low heat resistance, much lower than ABS, potential for oozing or warping due to its low heat resistance. Moving on to flexible materials. These filaments are a blend of plastic and rubber. As the name suggests, the material is elastic in nature, making the plastic flexible. The degree of elasticity depends on the chemical formulation. For example, some filaments can be partially flexible, like a car tire, or fully flexible, like a rubber band. Some pros of this material include flexibility and softness, long shelf life, and good impact resistance. Some cons are that the material can be difficult to print with due to its flexibility. It is also difficult to print more complex shapes as it is not rigid and strong. So, how do we access and design 3D objects? 3D printers are guided by a computer-aided design, also known as CAD. These designs can be created by the user using CAD software, or can be downloaded from various sites. These sites are often considered open source, as they can be accessed by any member of the general public. First, let's take a closer look at CAD software. What is CAD technology? Computer-aided design, or CAD, is the use of computer software to create or modify designs. CAD makes use of computer software programs to create physical objects that may be 2 or 3-dimensional. The objects can be accurately scaled using grids on the software. Once a design is complete, it can be saved as an electronic file, which is used by the 3D printer to create an object. The software allows users to view an object from multiple angles and rotate the diagram, allowing for improved visualization. In the healthcare field, CAD design files have been generated from medical imaging such as MRIs, CAT scans, and X-rays. There are a few benefits to using computer-aided design. Computer-aided design allows for better visualization of the finished product. Using CAD software, a user can create an object in parts that can then be assembled to allow for better visualization. Objects can be viewed as a whole or in separate parts. Overall, this also allows for a faster design process. CAD software reduces user error, as measurements can be entered electronically. The ability to view an object from various angles and in a 3D form also improves the accuracy, as the user has a better understanding of how the object fits together. Any design errors can be easily deleted or changed without the need for starting over. Another benefit of CAD software is that designs can be completed and saved to be edited or altered at a later stage, ultimately saving time for the end user. CAD software has specific properties that make the design process efficient and more accurate. For example, a user can automatically draw a circle by selecting the shape and choosing the diameter. At an educational level, the use of CAD software is rapidly replacing classes for producing hand drawings using protractors and compasses. Some challenges associated with computer-aided design are that CAD software requires a laptop or computer, which is not always feasible within the South African context. Although software is generally user-friendly, it does require some practice and time commitment in order to understand and use the software. Let's take a look at open source design sites. These are sites and forms of software that are openly accessible to the general public and can be used by individuals with limited or no experience in 3D printing technology. CAD software is generally used to create designs. These designs can then be distributed extensively using large online open source communities, with the end user having the opportunity to customize the model to meet specific needs.